Okay, this video is our introduction to multiple linear regression. This is the same simple linear regression that we've been studying for the past 2 weeks, but now there is more than one x variable. This might seem like a small and logical step to make. After all, if we were really studying pizza sales, then it seems very likely that it would depend on more than just student population. We would probably like to add more variables in order to get a more complete understanding of pizza sales. But this really changes everything. Our regression models are going to become far more powerful and useful, but often also far more complex. And this is the point in the class where we are going to start relying on heavy computing power to get things done. Most of my job now is to help you understand all of the computer output that we'll be dealing with. Even relatively simple multiple regression models are hard to visualize. Here's a nice, familiar, simple linear regression. There is one x variable, and all of our data points are plotted in the two-dimensional xy plane. And our best fit line is this simple straight line shown in blue. If we add just one more x variable, then the picture would look like this. The data points are graphed in three-dimensional space, where this axis is for the first x variable, this other axis is for the second x variable, and this last axis is for y. Additionally, our best fit line is no longer a line, it's a plane cutting through the cloud of data points. The small black lines between each point and the plane show the residuals for each data point. Residuals are still an important part of the regression analysis, as we'll see later. Now, if we add one more x variable, then I can even show you a picture of what it looks like. It exists in four-dimensional mathematical space that human beings aren't really equipped to perceive. So we have to really focus on the computational analysis since we physically cannot see the larger picture. Let's get into our regression assumptions. We let k denote the number of different x variables. Our model form assumption changes by adding each variable into the linear equation. There is still an intercept coefficient, and each x variable has its own slope coefficient. This form is called the general linear model. And then there is the random error term, which has the same assumptions as before: normally distributed, independent, and constant variance. We're going to look at an example about hotels. The y variable is operating margin, which is a measure of profitability, and there are 6 potential x variables that we are considering for our model, and they're all listed here. And here's where I also like to do things differently from the book. Many textbooks would label these variables as x1, x2, and so on up to x6. I prefer to give them names that help me remember what they are. For example, the first variable is the number of competing hotel rooms in the area. I decided to call this variable number instead of x1. When there are many variables to keep track of, this can help keep it all straight in your mind. Although this data exists in 7-dimensional space, which we can't perceive, it doesn't mean that we are helpless. We can begin to get a sense of the relationships by making scatter plots for each x variable. For example, here is the scatter plot for margin versus number. It has a noticeable downward trend, which makes practical sense. More competing hotel rooms should probably cause a decrease in operating margin. And here are the other 5 scatter plots. Some of them have noticeable trends, others don't. These plots can't tell us the whole story behind the data set, but it's a useful place to start. Now let's look at the computer output for this data set. In Excel, when you use the regression function in data analysis, there is nothing to stop you from selecting multiple columns when you enter the X input range. I just highlighted all 6 columns of X variables, and this is what the computer spit out. There are 3 general areas with important information: the regression statistics, the ANOVA table, and the t-tests section. Some of this information is connected to other parts of the output, and there are many similarities to the simple linear regression output as well. But there are, of course, important differences too, and I'll talk about each section in turn. The first part that I want to look at is the best fit coefficients down here at the bottom. These tell us the intercept and slope coefficients for the best fit curve. So the best fit curve equation looks like this. I've rounded most of the coefficients just so it will fit on the screen. But again, I prefer to write it with labels, so I would write number instead of x1 and so on, just to help me remember which each variable is. Now let's interpret the coefficients. This is very similar to what we did before, but with small changes. The intercept represents the expected value of y when all of the x variables are equal to 0. And again, this may or may not represent a realistic outcome. In our hotel example, it is pretty ridiculous to imagine a hotel with 0 competing rooms located 0 distance from downtown, but with 0 office space and 0 median income in the area. Anyway, and the slope coefficients again represent the expected change in y given an increase of 1 in the x variable. If we interpret the slope of the first variable, number, then we see that the expected operating margin decreases by the slope coefficient for each additional competing room, all else being equal. That last part, however, is new. In a multiple regression, when we focus on the slope of only one variable, then we are implying that the other variables are frozen. This is just a mental exercise in that we are trying to isolate the effect of only competing hotel rooms from all the other things that might have an effect on operating margin. For you mathematical minds out there, you might understand this as a partial derivative. Of course, in real life, this can be messy. For example, how could you possibly move a hotel closer to downtown, but with no change in the area's office space or median income? But that is a question best left until next video. Next, let's do a quick question involving the slope coefficient of income. We want to know how much median income would have to change in order for the expected operating margin to increase by 5, all else being equal. This is simply a question about the slope coefficient of income. We've already done questions like this before. Slope is equal to change in y over change in x. If the change in y is equal to 5, then the change in x must equal 12.1 or $12,100. Now let's take a quick look at the ANOVA table of multiple regression. The sums of squares are actually the same as before. The main difference is the degrees of freedom. The top row, or regression degrees of freedom, is now equal to k, the number of variables. The total degrees of freedom, however, remains the same, n minus 1, and the error is still the leftover amount. Of course, if you think about it, this is actually no different from before. This is the general form of the ANOVA table, and we have just spent the past 2 weeks studying the special case where k is equal to 1. And next I want to review these sums of squares calculations. Here I'm showing you just the first 10 rows of the data set. This will be enough to get the idea of the calculations. The 6 x variables are on the left, and the y variable margin is on the right. The formulas are exactly the same as before. They rely on y, y hat, and y bar. The only difference is that now the calculation of y hat is a bigger equation with 6 different inputs. Here is the first part of the equation, just to remind you. If we plug in the x values for each data point, then we'll get these values for y hat. So, for example, if we plug in all of the x values from the first row into the best fit curve equation, then we'll get the first y hat value of 47.8. And you can verify them for yourself. All right, so far we have y and y hat. Now we just need y bar and we'll be set. You aren't looking at the complete data set, so you cannot verify this, but the sample mean of operating margin is equal to 45.7. Now that we have our pieces in place, let's look at the sums of squares. We'll start with the regression sum of squares. That is y hat minus y bar squared. If we calculate that for each point, we get these numbers. And if we add them all up, we get the regression sum of squares. For the complete data set, it comes out to 3,123.8. Next, we'll do the error or residual sum of squares. That is y minus y hat squared. If we calculate that for each point, we get these numbers, and these add up to 2,825.6. At this point, we could calculate the total sum of squares by the formula, or just add up the regression and error sums of squares. Now that we know how the ANOVA table works, let's talk about what exactly it is testing. The ANOVA F test is for the overall model as a whole. The null hypothesis is that all the slope coefficients are equal to 0, which would mean that none of the x variables has any relationship with the y variable. A rejection would therefore mean that at least one of the x variables is related to y. And since at least something in the model is related to y, we could say that the model is statistically significant. Next, I want to look below the ANOVA table again at the slope coefficients. Each of them has a t-test that applies only to that variable. The hypothesis for each test is the same. We assume in the null hypothesis that the variable has a slope coefficient equal to 0, meaning that this variable is unrelated to y. And if we reject, then that variable is significantly related to y. The form of the t-test is just like in simple linear regression. We take the best fit slope and subtract the true slope, which is assumed to be 0, and then divide by the standard error. These standard errors are shown in the computer output. Right next to the best fit slope coefficients, so we can easily see each t-test calculation. And again, the degrees of freedom for the t-test come from the error degrees of freedom in the ANOVA table, and that is how these p-values are calculated. And we also have 95% confidence intervals for each slope coefficient over on the right. All right, looking at our 6T test, it looks like all but 2 of the variables are significantly related to operating margin. All but these 2. Now I want to return to the upper part of the computer output and talk about the regression statistics. Perhaps the most important number in this section is r squared. This is exactly the same as before, the SSR over the SST. And again, this is often quoted as the explained variance of this model. Since r squared is equal to 0.525, we could say something like 52.5% of the variance in operating margin is explained by its dependence on these 6 variables. The row called multiple r is just the square root of r. Square root of r squared. In simple linear regression, this would be the absolute value of the sample correlation. In multiple regression, it doesn't really have much meaning. And then the row called standard error, sorry the name got cut off, is the square root of the MSE. The MSE is still our best unbiased estimate of the constant variance, sigma squared. So this standard error is our estimate of sigma, or the constant standard deviation. This is interesting in its own right, and it plays a part in the standard error calculations for the slope coefficients, but we're not going to be using this number directly. The next part of the regression statistics is the adjusted R squared. This by itself is not a hugely important calculation, but it introduces a very important concept of multiple regression, so it deserves an extended look. This is the formula for the adjusted R squared that I prefer. It isn't the only formula, but it does the best job of showing what is happening. First, let's just plug in the numbers and see what we get. R squared is 0.525, N is 100, and K is 6. So the adjusted R squared is 494. Let's draw a picture to see what's going on. R squared is necessarily between 0 and 1. And so this distance on the right is equal to 1 minus R squared. And this shows up here in the formula. Next, this distance is multiplied by a fraction that is slightly bigger than 1. So the distance on the right is now slightly longer, and the adjusted R squared is always a bit less than R squared. Less than, not less than or equal to. The reason we calculate R squared is to penalize models that have excessive X variables. The definition of excessive is a bit subjective, and it depends on sample size too. For example, our hotel data has a sample size of 100 and 6 variables. That would generally not be considered excessive. And the adjusted R squared is only slightly lower than the R squared. However, if we had, say, 50 variables in our model, then that would certainly be excessive, and the adjusted R squared would be much lower than the R squared. Anyway, why is this important? Let's consider what would happen if we added a 7th variable into our model. And for example, let's say this variable is service staff. If we enter the data into the computer and redo the regression, then the total sum of squares wouldn't change. It only depends on y values and y bar. Adding another x variable would have no effect on this number. But here's the important thing. The regression sum of squares can only increase. If we add another x variable into the model, then the SSR cannot go down. At worst, it will just stay the same. But it is extremely rare in real life to find a perfectly zero correlation. So the SSR, and therefore R squared, will increase by a little bit. even if the variable isn't significantly related to y. Do you see the potential problem with this yet? It is desirable to have a model with a good fit, and there is nothing to stop someone from dumping all kinds of useless variables into the model just to artificially raise r squared. You could add such pointless variables as the hotel's address, the manager's shoe size, and the staff's average bowling score, and the fit of the model can only increase. This is basically statistical cheating, and therefore the adjusted r-square penalizes us for having more variables than is absolutely needed. In real life, the adjusted r-square is typically only slightly lower than r-square, and there's effectively no difference between them. But just be careful in case someday you come across an analysis with a big difference between them, and that would be a definite red flag. Speaking of having excessive variables, we have two variables in our hotel data that have non-significant t-tests. We prefer simple models to complex ones, all else being equal. So it makes sense for us to remove the unnecessary variables and only keep the important or significant ones. The process of removing unwanted variables is called backward selection. The basic idea is to remove one variable at a time, and the reason for this was explained in the next video, beginning with the largest p-value. After deleting the variable, we redo the regression and look at the new outputs, and we repeat this until all variables are significant. Here is our original output once again. The variable with the largest p-value is distance. So let's delete that variable and redo the regression. Here is the output with only the 5 remaining variables. We see that enrollment is now the largest p-value, so we delete it and redo the regression. And here is the output with the 4 remaining variables. The largest p-value now belongs to the variable nearest, but this is already significant, so we don't want to remove it. So we are done with backward selection, and this is the final model that we would use to analyze and make predictions for operating margin. This model has all of the important variables and none of the useless variables. I just want to point out that removing variables will necessarily cause the SSR and R-square to decrease. However, the R-square has only slightly decreased from 0.525 down to 0.505. And that just reinforces how useless distance and enrollment are to predicting operating margin. But finally, here is data on universities. You'll be analyzing this data in the 3 questions coming up, so take note of it. The Y variable is on the right, alumni giving rates. This is the percent of all graduates who donate money back to the school. And there are 3 X variables, graduation rate, percent of classes under 20, and student-faculty ratio. Note that the sample size is 48, but the complete data set isn't shown here. And here is the regression output for this data. I've blocked out some of the numbers, but there's enough information to figure out the rest. Good luck with that, and check out the next video.